I'm going to refer to this document, and I've been reading this maybe 3 months later than I should have been reading it, but I'm going to be referring to some of the items in this document, National Academy's report on digital twins. I'm also going to change the title of my talk slightly from the one that Victor had. I'm going to simply name the title Coordinated Analysis and Synthesis of Physical Systems, because what you will see as I go is that there is a parallel procedures for analysis and the synthesis. They mirror each other, as you will see as I go. And what would remain is the idea of physical systems, that they would all be applicable to physical systems. For many of you, you know my background. I'm actually a packaging person. You may be wondering what this talk is all about because this seems so different from semiconductors in general and packaging. Turns out I have a background in mechanics, in computational mechanics. And some of the topics that I'll address today, like multi-scale simulations, shape topology, optimal design, etc., they fall under computational mechanics. And machine learning also falls under it in this sense, in that in order to make shape topology, optimal design more efficient, we have often used in the past machine learning as a way to build surrogate models, use them for optimal design. There are other topics that I work on, such as continuum solid mechanics theory, and also in geometric modeling, and you'll see elements of this. And all of these are usually applied to electronics packaging. So that's the connection. The connection is this interest in computational mechanics. And interestingly, the National Academy of Sciences report has a very strong computational mechanics flavor to it, because the person who chaired that committee was a computational mechanician, mechanical engineer like me, a computational mechanician. So let me start off by what I mean by physical systems. The process optimization problem, I would argue, is mathematically analogous to design optimization. In other words, the procedures one uses for design optimization one can use them almost one for one for process optimization. So here in the design context, for instance, I might have an objective to minimize temperature, and I have a governing partial differential equation, which is really the Fourier law of heat conduction, and that I might use to, figure out which configuration is best for me, and I might do it systematically using an optimization algorithm. Similarly, if I take a process, I might want to optimize the etching rate. That might be my objective, and so I might want to maximize my etching rate. But it's also governed by PDEs that tell me the flow as well as temperature distribution inside the chamber. So in many ways, if you look at it purely from a mathematical point of view, they are quite analogous. So whatever procedure one comes up with for design optimization, one can apply for process optimization. This is going to be my thesis. But one challenge is many times for design, we have well-defined governing equations. Sometimes for very complex process, you may not have a well-defined governing equation, and that may be the only difference. But most of the time, we do have well-defined governing equations for processes like etching, deposition, lithography, etc., because those are governed by reaction diffusion equations. So those are well-defined. So with this, let me move on to the next. This was a slide that I had shown a month and a half ago when I had a chance to talk to this group. And I said that design and process optimization requires expensive analysis. That comes because we are trying to solve these PDEs, partial differential equations. And during the analysis process, any sort of synthesis or an evaluation step requires any sort of synthesis step requires an evaluation step, which is an analysis, which basically tells us how good the current state of design is, the current state is, and then we iterate on it using some sort of a search algorithm, and typically an optimization algorithm. And this step is what makes it expensive. And what we're trying to do oftentimes is to replace this analysis with surrogate models, machine learning models being one of them. One doesn't have to always use machine learning models. And as appropriate, we might use other models as well. So there is this going back and forth iteration between analysis and the synthesis steps, and that we try to do both during design optimization and process optimization. And I showed this picture a month and a half ago, and Jim said this doesn't quite look like the idea of a digital twin that's there in the National Academy of Sciences document that I just pointed to at the beginning of my talk, because I said, well, one would basically use either data generated from experiments, which are harder, which are more difficult to do, or from simulations, or simply analytical solutions to your theory to generate data, and that data in turn with training becomes our ML models. Now here I'm going to classify the nature of the data here as physical if it comes from experiments, virtual if it comes from computational models or ML models. I'm going to treat them equally. And generally, physical experiments are more expensive, more time consuming, generally speaking. And computational models are less expensive, and theoretical models are even less expensive. And the belief is ML models would be virtually free for us to use. They may be very expensive to develop, but they are virtually free for us to use. That's the idea behind all the the suggestion for using ML models, machine learning models. I wouldn't use the word AI because I don't quite know what that means. I would use the word ML because I understand that far better. I'm going to quote here something directly from the National Academy of Sciences document. And the quote here is the computational models are characterized by parameters. This is an important point. All computation models are characterized by parameters that are virtual representation of attributes such as geometry and constitutive properties of the physical counterpart. So if you're a computational mechanician, this would be very, very easy for you to follow. This is exactly what computational mechanicians do. They have a geometry, a domain, and they have constitutive behavior, material behavior, and they solve for physical behavior in that domain with the material behavior. And it corresponds to its there are boundary conditions, initial conditions, all that will help us determine the behavior. External factors that influence the physical counterpart and transfer coefficients between resolved processes and parameterized unresolved processes. So this is a quote. And there is another important statement in that document, that is that the virtual representation must be fit for purpose, whether one uses full simulation models or one uses ML models depends on the purpose. If I can afford the time, then full simulation models are always better than ML models. Now, let me go on to the definition of the digital twin. The definition that's there in the National Academy of Sciences document. Again, this is something that you may be very familiar with. So this definition has a physical counterpart to a virtual representation, and there is a continuous feedback between the two. And I indicated that with these two extra arrows that I didn't have the last time. And so I added that extra. And then there is a statement in the document that digital twin is more than just simulation and modeling. And I add a but here because then it goes on to say the key elements that comprise a digital twin include modeling and simulation to create a virtual representation of a physical counterpart and a bidirectional interaction between the virtual and the physical. I think this is the part that they emphasize by saying that it's more than just simulation and modeling. It doesn't mean that modeling and simulation are not important. That is still the number one element of a digital twin. then this bidirectional interaction forms a feedback loop, etc., etc. And then finally, there is another important item in that report, and that is emphasis on verification, validation, and uncertainty quantification is essential for digital twins. Now, we've not really talked much about this in our deep dives or in our Smart USA discussion as well, but this is a key element that's emphasized quite a bit. And this was, I should take that back slightly. Surya Kalidendi's presentation did emphasize uncertainty quantification. It was an uncertainty quantification, but we do need to bring a little bit more focus to that. And there's another statement relating to verification, validation, and uncertainty quantification. They abbreviate it with VVUQ, and they keep emphasizing this. There's a page or more on VVUQ, the importance of a rigorous VVUQ process for a potential powerful tool such as the digital twin cannot be overstated. So these are all some of the statements that I gleaned from the NAS report. So let me go on to the topic more close to the topic of today. So if I think about this as being a unit digital twin, what we develop here as a unit digital twin based on experiments on a specific equipment, specific computational model, and an ML model that tries to mimic the experiments and the computational model. And we talk about how this is built in this particular slide. The question is, how can I then pull together many such digital twins to create what we are calling as a digital backbone? So how might that backbone look like? Connecting, I'm going to call this connecting virtual representations, the challenge of digital backbone. This is my description of this. And again, some of these definitions that I will use between hierarchical, non-hierarchical, etc., are my own definitions. You might disagree with me, and we can have a discussion on that. But let me start with these two definitions here. I'm going to say that there are two possible ways you can pull together or have digital twins interact with each other. One might be a hierarchical interaction. So I might have a system digital twin, if you will, or the backbone digital twin, if you will, that interacts with unit digital twins 2 and 3. And it always has to be bidirectional. It cannot be unidirectional. Just the physical problem itself will dictate it to be bidirectional, as you will see later. It cannot be single one directional. So it has to be bidirectional. Or you could have them non-hierarchically arranged. In other words, there is no parent digital twin and a child digital twin. They all have equal importance, equal level, if you will. So this could be a non-hierarchical interaction. Now, then the question is, what information is transferred between these digital twins, between these hierarchically arranged digital twins or non-hierarchically arranged digital twins? What information is transferred, and what information to exchange will be also be informed by how do you ensure privacy? I don't want to share all my information between these digital twins. I want to provide the least amount of information so I can infer all the properties of my child digital twins without revealing any of the information about the parent digital twin. I want to provide the least amount of information here. And I also, in turn, query something about the nature of this child digital twin so I can get an idea about this child digital twin. You can do this in physical systems, as I will show you later. And there are specific quantities one needs to pass back and forth on physical systems, and I'll talk about that later. And I also want to get some more information. The other information, by the way, this hierarchy can extend to multiple levels. It doesn't have to be just 2 levels. It can be extended to multiple levels. Similarly, non-hierarchical, you could have many, many more. So I'll also talk later about the need for how would you do verification, validation, and uncertainty quantification. What information should I pass and what information do I get back? in order for me to assess the uncertainty in, for instance, in any one of these digital twins, what if there was a malicious actor which somehow changed this digital twin maliciously so my system is messed up? So how can I assess, how can I build confidence about any one of these digital twins? We know how to do that for physical systems. I'll show how we can do that for physical systems. And for digital twins, we might be able to take inspiration from how we can do it for physical systems and extend it to digital twins. So that's going to be my argument today. So in other words, how do I ensure through this uncertainty quantification, how do I ensure the validity of my backbone? That's another important question for us to address. The other point that I want to make in this slide is the hierarchy could be in the system or in procedure. In other words, this could replicate a physical system, or it could also be just simply a procedural hierarchy. So I'll address both of them. So again, I'm going to use some examples to make my points today. I'm going to use 3 sets of examples, if you will. So first is I'm going to talk about one where I have hierarchy both in the system and procedure. And this, again, a lot of these are examples from some prior work in my research group. So I'm going to talk about geometry-based analysis. There is a hierarchy in geometry construction in mechanical CAD. This is, again, going back to my mechanical CAD background. So if you look at the way you construct a geometrical part in a CAD system, like Pro-E or SolidWorks, what you would do is this is procedurally done, not necessarily, you no longer have what are called pure constructive solid geometry CAD systems. You have mostly what are called BREP, boundary representation CAD systems, where you represent the final geometry by the skin, the boundary, as opposed to, but behind scenes, there's usually a constructive solid geometry operation that goes on to build a geometry. Let's say I want to build a geometry of this nature. I might start with primitive geometries that are very simple, and then I might construct a set of, I might do a set of set theoretic operations on point clouds defined on these individual primitives. So for instance, this piece here is intersection between the cylinder and this wedge. That gives me this piece here. Then I union it with this rectangle to get this piece here. And then I subtract this whole region here to get the final geometry. And this is typically the process. There's usually a history tree, and this is called the constructive solid geometry procedure. And then what we would do is to mesh this and carry out analysis. We throw away the whole geometry and basically go with this mesh as a surrogate for the geometry and carry out analysis. Now the question is, what if my hole size were to be made larger or something else were to change in the geometry? Then you start all over again in the CAD. Basically, you start with the primitives again, you construct the final geometry, mesh it, and you have to reanalyze it. So one of the questions that the community, the computational mechanics community has struggled with is there any way we can bring together the analysis and the geometry more tightly so you don't have to go back to step 1 to reconstruct the geometry and reanalyze? And one approach is something that we worked on, and now more popularly, these kinds of approaches are called isogeometric analysis. Although our work was before the term isogeometric analysis was coined. It was 1 year before the term isogeometric analysis was coined. And we said that instead of thinking of these primitives as point clouds, you could basically describe within them a functional description, a function that then could be composed in a complicated manner as long as its primitive functions belong to certain spaces that assures that the composed function also has certain properties. Now, instead of constructing the final geometry, meshing and analyzing, what we are saying is we have behavioral approximations in my primitives that interact to describe how the final piece might look like. It's sort of like saying I have ingredients for food. I don't cook the food, but I can sort of taste how the food might look like without actually putting things together. So that's sort of a crude analogy that I can give you. And so you can construct this sort of an approximation. So this approximation mirrors, this behavioral approximation mirrors both the geometry and material approximations that you might construct on this. So this is, again, a hierarchical there is a hierarchy in physical hierarchy, followed by a procedural hierarchy as well. The procedural hierarchy is how you compose them to construct an approximation in the final domain. Then the question comes, and this question is very relevant for digital twins as well. Now, I have constructed approximations on my primitives, and think of these primitives as my individual digital twins. So I have constructed these approximations. How do I know that the final approximation that's constructed based on these individual primitive approximations is valid? So I need to somehow prove that the final approximation is valid. In other words, this approximation that I have of a system-wide of this solution on the whole object is valid. And there is a way to do that, and there's a proof for that. And that proof is if I have my local approximations, think of these as my unit digital twins, and if they have local approximations, as long as these local approximations obey partition of unity property that assure boundedness of global approximation. So we need something like this for digital twins, backbones. I don't know what it is yet, but this is something that we would need for digital twins as well. How do I assure that the final digital twin that I construct out of my primitive digital twins is valid approximation for my systems of flow of processes? That's something we need to build for digital twins as well. But we know how to do that for behavioral modeling that I just showed. So I'll give you an example here, particulate tints. This is close to semiconductors. I'll have a few examples that are close to semiconductors that are applications of the techniques that I described here. So this is a particulate tint.
Dry steps.
This is a particulate tint where you have particles and matrix. So this is alumina particles in silicon or epoxy matrix. And this was work we did with the GE about 22 years ago. And when you do experiments, what you find is there are classical models, Maxwell's expression, Rayleigh's expression for these particulate arrangements. And what you find is that the experiments don't quite match the classical models, especially when the volume fractions, when the volume loading of pillars go beyond 30%. And the question often is it because you didn't capture the spatial arrangement of particles or because there is a poor interface between the particle and the matrix? This question keeps coming over and over again. And the difficulty with answering this question, especially answering the spatial arrangement of particles, is it's very difficult to model computationally spatial arrangement of particles. So what we did was to use the computation procedure that I described, the hierarchical procedure, and then model different arrangements of this particle, many such arrangements, usually 30 such arrangements behind each square dot that you see here, the square dot, which is a 3D numerical solutions. And you find that you can answer quite well the experimental reason, the experimental data, why the experimental data doesn't match to the classical models. And that's because you're not capturing the particle arrangement. And there is actually a near percolation transport. When particles are in close proximity, they transmit energy much better when they are farther apart because the matrix is so poorly conducting compared to the particles. So you can explain that with models like this. So that's an example of, again, an application of the hierarchy in geometry mirrored by hierarchy in behavior. So here the procedure as well as the system is hierarchical. Next, I'll give an example. You have hierarchical analysis or synthesis procedure. The procedure is hierarchical, but the system is non-hierarchical. So let me give an example of this. So you have, if I take system level synthesis of complex systems like system of systems, as people like to call them, aircrafts or automotive, these systems are complex. They include multiple interacting subsystems. And subsystems are independently designed often, and data sharing is limited. Oftentimes, you might have a integrator vendor type arrangement where the integrator does not want to share any data with the vendor, and the vendor does not want to share proprietary data with the integrator. So the data sharing is limited. You don't want to, for instance, pass back and forth your CAD models. And those are huge, and it doesn't make sense to share them back and forth. So how do you design in these kinds of situations? So, but the interaction of subsystems is very important. How do you go about designing in these kinds of situations? I will use design as motivation. Like I said in the beginning, design and process in my mind are they're analogous mathematically. They're not that different mathematically. So I'll start with a motivation. There is an idea in analysis in computational mechanics called this idea of nodal condensation, and this only works in linear systems. Excuse me. Let's say I have a discretized governing equation of this form. Most physical systems, at least a static, quasi-static physical system, can be represented with this kind of a governing equation, k times u equals f. Even though it starts with a differential equation, it can be reduced to this form by discretization. And then you can partition it into external and internal variables. In other words, just partition the matrix by rearranging rows and columns so that the variables that are external, meaning the ones that occur at the interface between the parts, and those that are internal to the part. So you can rearrange the rows and columns so you get these partitioned matrix, and corresponding the forcing vector will also get partitioned. And then you can describe the internal variables in terms of the external variables in a straightforward manner, like I've shown here. And then you can actually substitute that back and you can solve for the external variables. Why do we do this? This is actually a two-level process. The reason why we do that is because the number of degrees of freedom that you will have in the whole system is so large, you don't want to solve the whole problem all at once. You want to solve for the variables at the interface, and then you want to back calculate what might be the response interior to the system. You want to think of your whole system as consisting of many parts, and you want to solve for the details of the parts later. So it's a two-level solution process. There is no hierarchy in the system itself, in the physical system, but the solution process has a two-level hierarchy here. And it turns out you can extend this two-level solution process, analysis process, to synthesis as well. And I'm just illustrating this with a picture here. So here, for instance, if I have a piston and a crank, and the crank itself, the connecting rod itself can be modeled in hierarchically, geometrically. But here, if you look at the assembly doesn't have hierarchy anymore. So the parts don't have hierarchy anymore. And it turns out these kinds of problems, you can actually carry out a two-level hierarchical synthesis, analysis and synthesis process. I'm not getting into the detail because the detail is quite messy, mathematically messy. But the idea is this: you can construct a global system. Think of this as my digital backbone. So I can construct these matrices from the subsystems. This is again works for linear systems. From the subsystems provide me information for me to construct it, but the subsystems don't know anything else about the other subsystems. And then I have some variables that basically are linking global variables. These variables, if I solve for them, I can solve, if I pass them to this subsystem, then the subsystems can figure out what the behavior inside the subsystem is going to be. But it has no clue otherwise. Otherwise, it has no idea about what the overall system response would be. So we have these surrogate now, new variables. These variables will define the response within each of these subsystems, this alpha and gamma. Now, it turns out, supposing phi is a design parameter, and this design parameter changes in one subsystem, then I can also calculate in exactly analogous manner the sensitivity of this parameter gamma and alpha. This is all described in this paper. So this is of gamma and alpha in exactly the same way that I do evaluation of gamma and alpha. It turns out the coefficient matrix is exactly the same thing, turns out. So now I have a solution to the sensitivity of my parameters, the global parameters, that when I pass to my subsystem, then I can evaluate not only the behavior, but also the sensitivity of the behavior to the design change in some other subsystem, in any subsystem. So this is there is no exchange of geometry or material information between subsystem and subsystem in this process. So going back to my question earlier on when we talked about digital twins, and I asked the question, what information should we pass between the digital twins? This gamma and alpha are the information that you will be passing between your digital backbone and your unit digital twins. Because if I define these parameters, if I calculate these parameters, every subsystem is defined. So we need to find an analogous way of doing this for digital twin backbones, but you can do this for physical systems. So, and why do we need these sensitivities? You might ask the question, why do I need the sensitivities? And this is uncertainty analysis 101. My apologies to Surya if he's on the audience, because he might be insulted by this. To a first order, there is a method called first order second moment method, and where I take any arbitrary function, any performance function, like this might be my manufacturing yield or reliability, I can approximate it to a first order using Taylor series, and then I can construct, using this first order approximation, the statistical analysis to calculate my expected value of that function, which basically turns out to be the function evaluated at its mean, or calculate the variance of that function, in which case I need both the sensitivity and the covariance matrix. So if I have sensitivities, I can tell you uncertainty. I can quantify uncertainty. So sensitivity is actually the first step to quantifying uncertainty. So again, when you have digital twins, if I want to quantify uncertainty, I need sensitivities. That's really the point that I want to make. Okay, finally, I'm going to talk about a non-hierarchical procedure, but a hierarchical system. Again, this is an example of multi-scale modeling. I know one of the things that we've talked about quite a bit is the need for multi-scale, multi-physics modeling. Multi-physics modeling is more sort of obvious for most people, but multi-scale modeling is actually equally important, as I will show you. Multi-scale modeling, especially at package level, needs to span 5 to 8 orders of magnitude in length scale. So it's very, very important. And again, the sort of thinking that I described to you, hierarchical, here, for instance, I'm going to have a non-hierarchical procedure, but I have a hierarchical system. And that is what is going to underlie the multi-scale modeling procedure that I will describe. I'll motivate this with physical problem. It actually was motivated by an example from one of the SRC member companies. So, and it was an SRC project. So this, what I'm going to describe today, this last example is actually an SRC project some years ago. So we have a structured aluminum line molded package, and some structures failed after 500 plus thermal cycles, not at time zero, but after 500 plus thermal cycles. Ramesh, you have a question I can answer now, or you want me to?
No, just lining up.
Yeah, go ahead, Ganesh. I think your lecture is so good that I don't want to interrupt you.
Thank you. So this is the structure that there was a real failure problem, and the failure didn't occur on the outermost signal line, but actually one before the outermost signal line, interestingly. It was very geometry dependent. It was very specific, unique. And what were the mechanistic causes of the film cracking? This was a TIOS that was cracking. We didn't quite understand why that was cracking, etc. So this is actually caused by the mold compound. So this is an example of chip package interaction. So you were seeing back end of line cracks because of molding process and because of the properties of the mold compound. The mold compounds are very strange materials. They have temperature dependent CTEs that were causing out stress in a certain way that was causing these cracks. So in order to do this, you need to be able to link length scales, package level length scales, and the molding process down the stress accumulation and the thermocycling process to figure out why cracks originate specifically in this particular corner here and not anywhere else, and why that was related to wider aluminum lines. In order to do this sort of length scale linking, there's a classical process. It's called global local FE models. So in other words, you construct a global model, take the boundary displacements around in the global model around the region of interest to you, apply them to the local model, forget the global model. In other words, you assume that because your global model is so big compared to your local model, your boundary conditions on your local model don't change. That's the assumption you make. So that there is, in other words, there is no feedback. If there was a crack that was propagating, there's no feedback to the global model to tell the global model, that stiffness is no longer the same as what it was before, and therefore something has happened. So if you were to do it with, if you were to actually model the crack propagation, it turns out, this is some work that we did about 20 years ago. So what you'll find is the crack fronts are not accurate. So by the way, we were among the first groups to actually track the crack propagation, fatigue crack propagation in solder joints. This was the work that did that. So, but however, if you have a two-way coupled model, then the crack front is a lot more accurate. So even though a solder joint might look insignificant in terms of volume, in terms of its stiffness relative to the overall structure, it does influence the overall structure. There is actually feedback to the overall structure. And if you don't capture that back and forth feedback, then you would not be able to predict the failures accurately. So I'm going to skip through some of these details. So in general, if you don't have this sort of two-way coupling, your predictions would be inaccurate. So I'm going to skip through all this. In general, if you want to model this multi-scale, you have fully refined models, which might require millions and millions of degrees of freedom. In other words, one model, no partitioning. Or you could have a global local partitioning. There is no feedback. Or there is a third approach, which is really a domain decomposition, which is, again, an area that developed to do parallel finite element analysis. In other words, how do I solve PDEs on a parallel computer? That's where it started. I would divide my mesh into multiple pieces, send each piece to a different processor on a parallel computer, and I would solve it. And that approach is domain decomposition. Here, there is no hierarchy anymore between my subdomains. They're all non-hierarchical. However, I could turn this into a hierarchy, as you will see. So which is what we did. We developed a theory, and this is again published, and thanks to SRC for sponsoring this work, and the SRC member company, and we are very grateful to them for sponsoring this work and guiding us. So again, now you can turn this domain decomposition problem actually into a hierarchical problem. So in other words, I have a region here that's of interest to me. That region is blown up here. And in that region, there's a small port where the crack actually initiates and grows. This is the TEOS in which the crack initiates and grows. So we can turn that, the non-hierarchical approach into a geometrical hierarchy, but the process itself would not be hierarchical. And there's a lot of details here on how we can do this. Another advantage of this, the way we approach this problem, is that it turned out we could actually have one piece of the model modeled in a Simulia abacus, another piece modeled in ANSYS. You can combine them, mix and match them, and it turns out you actually get that sort of coupling through this theory that I described and the modeling, the code that I described. It's a MATLAB code to couple them. If this coupled analysis actually gives you a solution that's quite close to the full refined analysis compared to the local local modeling approach that I described earlier. What you're tracking here is the crack growth due to the bump shear process. So again, you can mix and match codes, etc. Okay, so one last slide on this topic. Now, if I have this sort of an approach where I have a physical system hierarchy, but procedurally there is no hierarchy in this case, then I can actually, for each piece, I can actually construct a machine learning model. And this way I can affect multi-scale modeling for these kinds of systems. Now I can link package length scales where I have mold compound that's causing crack at a very small length scale. I can link them, but I can evaluate them much more quickly. I can probably do it during the design stage, early design exploration stage as well, if I could do this. So that's the ultimate goal. So this is my last slide. So I want to reemphasize that the key elements of the digital twin are modeling and simulation. I mean, I'm somewhat biased in that assessment, as you can tell. So, but bidirectional interaction between virtual and the physical is important. We have not discussed very much verification, validation, and uncertainty quantification, and this is critical, and it's dependent on sensitivity of global variables to parameter changes. And this is important also to ensure trust, unit digital twin trust. So critical decisions for building a digital twin backbone are what information to pass to unit digital twins, how to carry out verification, validation, and uncertainty quantification, and finally, hierarchical and non-hierarchical strategies for analysis of physical systems may provide insights into building a digital twin backbone. So I'll stop there. Thank you.
Thank you very much, Ganesh. It was indeed very interesting, and I just could not. Well, I really was very engaged in listening. Let's put it this way, and actually some eye-opening statements. Simple, but I would say we need to think more of this, which means we assume that when we connect all these links together, they will work as intended, and there are no reason actually to believe in this, right? And I'm impressed with your mechanical analogy. Many good things. So, but I see people lining up. So let's do questions. Ramesh.
Yeah, excellent presentation, Ganesh. And I particularly like your treatment in the beginning, which gives this generic and holistic view of the digital twin. So connecting it back to one of the discussions in the last meeting was about these two aspects of digital twin that we need to deal with in MAP 2.0. One is about this as a application applicable to many systems, and how semiconductors is providing the architecture, processing architecture, for example, for supporting those. So I think in that regard, my opinion is it can be either a separate chapter on its own that can go through the generic aspect, or good part can be in the chapter 4 on processing. And then semiconductors as a user, or using for our own purpose of design and manufacturing of semiconductors. So that was just my comment about very good overview you provided. Now, the one quick question I had was, you talked nicely about this hierarchical aspect of this modeling, right? And need to have this bidirectional communication between them. I'm just wondering, within this hierarchical view, can we also think of hybrid view of these twins, which means these twins, rather than just mirroring each other, can be more cooperating?
There is some information that it's a question of how much information, who's providing who the information, right? So each side has to provide some information.
Yeah, I mean, just to give you a quick example, when we do verification, for example, we have hybrid environment. Certain things are in model, certain things are in actual design. And so you can replace parts of the two systems where one is easier to do or more efficient to do between the two systems. So anyway, something to look into.
Sure. I need to think about it from this is all purely from a digital twin model perspective, not so much from the physical twin perspective. Because we were talking about we are talking about interactions between the digital twins, but what hybrid means, it's not 100% clear to me, Ramesh. But maybe I can have an offline discussion with you to understand better.
Okay, Sadas.
Thanks, Ganesh, for a nice presentation. I had a comment on your statement regarding design and processing. Just an observation that what we have observed is there are 3 levels of complexity difference between design and processing. One you mentioned, the models may be unknown in one while are known in the design. The other is actually chemistry is an important part of any processing. Without chemistry, you can't get the right thing right, because the third is dynamical nature. Because processing has a time-dependent element, which I have not seen, at least the designers I worked with, deal with them in terms of state representations, but not dynamical.
So just to comment on that, if you look at my differential equation, the left-hand side is static and the right-hand side has a time variable.
No, I know. I saw the equation, but I thought I was just referring to your
Sure.
about saying between between design and processing. You said models may not be known. That may be the only difference. I thought you said that was all I was referring.
No, all valid points.
Okay. No, I agree with it, and I know you are very much aware of this, but I just wanted because this is manufacturing and digital twin from the NIST perspective, we just want to make sure we capture all the aspects, at least the ones which we think we are relevant. And as you mentioned, they may be too hard or models may not be known. Just need to think about them. That's all.
Right. All I wanted to say is that mathematically they are analogous.
Right.
So in terms of how the
Yeah.
optimization problem itself, they are mathematically analogous. That's all
Yeah.
I wanted to say. The challenges is one apply to the other as well.
Thank
Jim?
Yes, Ganesh, I wanted to applaud your slide on the unit digital twin. And it may explain why there's so much interest now in digital twins again, because of the advent of new capabilities from the AI and machine learning world. I mean, the reality is digital twins have been around for a long time, with many statistical methods and other types of data analysis techniques. But the progress in AI and machine learning, and as you pointed out, with machine learning models perhaps being much more economical and more practical, maybe more feasible for some of these complex systems, it now has created new energy, new interest in digital twins. I was wondering if you could share additional thoughts on what has changed that creates this interest. I do note that in the National Academy report, there certainly is reference to AI and machine learning, but it's not necessarily the focus, right?
No, in fact, they are very cautious in recommending ML.
Yes.
I would slightly differ from what you said, Jim, in that I don't think the ML model capability has changed dramatically in 25 years. So we are still using the same ML techniques that we were using 25 years. However, the bidirectionality is really the new part. The need for instantaneous feedback to correct the physical experiment and the need for instantaneous data from the experiments to change the ML model. That's the new part. I don't think the ML models themselves have changed. Without meaning to toot my own horn, I had a chance to talk to a distinguished group of people who were making decisions, policy decisions. A week and a half ago, a few of us had a chance to make, and the same question came out. What is it that you control? Do you control algorithms? Do you control data? What do you control? If, for instance, for EDA, specifically for EDA. So I think you know what I'm referring to. So then my view is it's not the models, because the models algorithms are very well known. They haven't changed at all in 25 years. What you do control is the fidelity of the data. So you do need to keep the fidelity of the data. That is more important than actually the models or algorithms. Those are easy to create, but the data is not easy to create.
Yeah. Great, thank you.
Kanad?
Ganesh, fantastic presentation. Bring up the importance of the computational models in digital twinning. One quick comment. The continuous exchange between the physical model and the virtual, virtual model and the physical counterpart, that is not necessarily continuous. In many cases, you may reach a convergence, and that exchange may be no longer necessary. The only place where it's necessary is, to track deviations, right?
Correct. I mean, like in any feedback loop, right?
Exactly.
So when the error goes to zero, then you no longer need to do any correction.
Right. This kind of implies it's continuous. There is, it's really, continuous. Yes, the data is coming in, but you react to it only when you have to.
As needed. Yep, absolutely.
Thank you.